Okay, بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. السلام عليكم everyone. Good morning. I know. I know it's a lot to take, especially for those who are trying it for the first time. But studying that late at night is not that bad. Okay, so it's also we have the best slot, so there are people that still start after us. So you're lucky to have this. I'm lucky at least. So we might have another class. So first of all, Ramadan Mubarak. May Allah accept from everyone. So today, inshallah, we're going to be starting topic number 3. So we're done with topic number 1, mathematical foundations. Topic number 2, about the modeling of one rigid body. Today, inshallah, we're going to be seeing, now we're going to be using this rigid body and all of the tools that we discussed to start to talk about robotics. So in topic number 3, we're going to be looking at modeling fixed base manipulators. And actually, we're going to have even one more lecture. If time permits, we're going to be able to look also at drones, and hopefully, if time even permits, but I doubt, we can look at floating base manipulators. Okay, so today, inshallah, lecture will be so let's start with the motivation and some terminology in general. What we'll be doing. So topic number 3, we're going to be focusing on the kinematic and the dynamic modeling of fixed based open chain manipulators. So when we say open chain manipulators, we mean this kind of robots. We don't mean this kind of robots. So these kind of robots, they are called closed chain or parallel robots. So this will not be able to have time for them, even though they are in the book using the same tools that we're learning. And we're not going to have time to look at floating base manipulators. Okay, so with the ones that the base is actually moving. And this moving base, it could be on the ground, it could be in the air, it could be underwater, it could be in space. So you can have really a generic framework for this kind of robots. These are actually the current state of the art. Usually, there's a lot of open problems here if you want to do research, and so on and so forth. On the other hand, fixed base manipulators is really very well understood. It's a very mature topic. Okay, if you say that you're going to do research with fixed base manipulators, it better be something really good, or something maybe with AI, and you're really using this as a test case. But everything with fixed base manipulators is well understood. It's a very mature topic in that respect.
I think it's not the Lie group, right? It will be general because
I have no idea. That's a good question. I don't know whether the configuration space will be a Lie group. I don't know. You can take a look at the book, but that's actually a very nice topic.
Because this constraint, I think it will be not the Lie group.
I have no idea. I really. You're going to see actually, even for fixed base manipulators, the configuration manifold is not even a Lie group in that sense. So even don't have a Lie, you're going to see hopefully the link today. So what we're going to be doing today, inshallah. So we have the first, let's say, component that we can build robots with, which is the rigid body. So hopefully you understand now how to describe a rigid body, how to model the dynamics of a rigid body. What we're missing here to do robotics, okay, is actually joints. So when you have two rigid bodies, for example, rigid body 1 and rigid body 2, and there's a joint connecting these two, the joint will actually constrain the motion of these two rigid bodies. We're going to be looking at ideal joints, so we're not going to be including friction and more complicated and actuation and stuff like that, but it's easy actually to add them. And an ideal joint is also known as a kinematic pair because it simply is a kinematic relation between the two rigid bodies that restricts the relative twist. That's it. So if you have a joint between the two rigid bodies, you'll find that the relative twist, so the twist of body 1 with respect to body 2, or 2 with respect to 1, doesn't matter, expressed in any frame, this will be actually a restricted motion. You're not allowed to have any 6 numbers. You're going to have a restricted number. Okay, so restricted numbers. So that's the idea of what a joint is. And simply when you say the degrees of freedom of a joint, you actually mean the number of independent coordinates of this relative twist. Okay. So this is usually the terminology that we're going to be looking at, we're going to be using, and the first topic we're going to be looking at, so the first lecture of topic number 3 will be actually talking about joints and how to model them. Then afterwards, we're going to be looking at the forward kinematics. So the forward kinematics of a robot refers to the calculation of the position and orientation, between quotes, or the pose of the end effector frame, given 2 things. You need to specify the robot's geometry, for example, all of the length of the links, what kind of links, what kind of joints do you have? For example, if you have prismatic joints, if you have revolute joints, and others. And also you need to provide the joint configurations. So let's assume, for example, we have n joints. Okay, and these n joints are connecting. Okay, n+1 rigid bodies. Then mathematically, the forward kinematics is simply the map that would take the Q's and will send you to a space. Let's call it W. This is usually called the workspace of the robot. And essentially, it's actually a subspace of SE3. It's not all of it, could be all of SE3. This is the symbol here. So it could be a whole of SE3, which means that the end effector can reach anywhere. Okay, the end effector pose can reach anywhere, or in general, it can be limited. For example, if you take a look at this 3-link robot arm, can it go out of the board? No. So you see, it cannot go actually to any pose of SE3. So for example, the pose of the robot of the end effector will always have something like this. It can move like this, okay, and it can have a different orientation, but it can never get out of board. So it cannot be SE3. This is just an example of what the workspace would be. And usually the configuration space itself, okay, so or the joint space, so usually called the configuration space or the joint space, is simply where all of the joints live, all of the joint angles live. And here, for example, if you're given this kind of robot, okay, this 3-link planar robot with 3 revolute joints, it's an open chain, and simply the pose of the end effector, which is frame 4 with respect to the base, which is frame 0, so H4 with respect to 0, is simply given by a rotation matrix of this form and 2 values here, x and y. We cannot have any z, so the value of z, assuming the z is out of the board, so z will always be 0, and the x and the y and the phi here, which is the angle of simply the end effector, are given by these 3 expressions. If you look at them just by, if you eyeball them, it's actually very, it makes sense, right? You just have some L1 cosine plus L2 cosine plus L3 cosine in the x, and L1 sine, L2 sine, L3 sine in the y direction, and the angle phi is simply the sum of the 3 angles. This is usually, the map. You see, this is a map that takes θ1, θ2, and θ3 as inputs. It's also a function of the L's, the length of the links, and it gives you, in the end, x and y and phi, which in the end make up the homogeneous transformation from 4 to 0 of the end effect. This is usually what's known as the forward kinematics map. We're going to be seeing, of course, more. This will not be the way of how we do it. So this is simply, you can do it with using simple trigonometry, but this simple tool will fail when you go to complex robots. So the whole idea of this topic is to level up the math in the same way that we did before and use some stuff from Lie groups so that we can even handle any kind of robot that you can face. Okay, any kind of open chain, to be precise. So that's the forward kinematics. The next topic after forward kinematics, you need to look at differential or velocity kinematics. So differential or velocity kinematics are 2 names for the same thing. And if the forward kinematics is a map from the joint configuration Q to the end effector pose HE to 0, then the differential or velocity kinematics is simply the differential of this map. If you have a map from Q to H, then the differential of that map will be from Q dot to H dot, where Q dot lives in the tangent space of Q at the point Q, and the H dot lives in the tangent space, as you know, to SE3. Okay. Of course, it will be again in the workspace, not of all SE3. And as you know, H dot from now on, we have a 1-to-1 map between H dot and elements of the algebra. Okay, and this element of the algebra is simply what you call the twist. So we can also use, because geometrically, we can represent a map from Q dots to a map, to the twists. Okay, so the twist of the end effector with respect to the 0 frame, with respect to the base of the robot. And we can express it anywhere. So the VE with respect to 0, this is usually the end effector twist, while the Q dot is simply the joint velocities. So the differential kinematics will be a map that will take you from Q dot to the twist. Okay. And afterwards, everything will be very straightforward. If we're able to do this geometrically, okay, that's the whole idea. How do we represent this geometrically? So this is the plan for topic number 3. Inshallah, we're going to have 4 lectures. The first one, which is today on the modeling of the ideal joints. Lecture number 14 next week, inshallah, will be on the forward and differential kinematics all at once. And then we're going to have enough time, inshallah, to look at dynamics and look at the several examples along the way. Okay. You're going to have some homework. We're going to be starting to use MATLAB, to do this actually to help us in like confirming the theoretical results that we're doing here. And this will be a big part of what you're going to be doing in the project. Okay, using this information, you can already start working on your first deliverable of the project. Okay, and we're going to be talking about this later on. Okay. Yes.
What is the velocity that you mentioned in the previous slide?
Shoot, this one?
Yes.
Which one here? This V is the twist of the end effector with respect to the base. Okay. The E with respect to 0. Okay. So we're going to be looking now at something. We're going to be introducing a little bit of math, but again, you should be familiar with how it goes. Okay, we're going to be introducing a lot of new terminology, some abstract stuff. You're going to be seeing how this abstract stuff, which is here known as displacement subgroups, how this will enable us later on to model joints. Okay, this actually idea of displacement subgroups will enable us to in one page with really just very few abstract concepts to model all kinds of joints that you just saw on the board in a while. Okay, and we're going to have examples along the way. So when you say I have two rigid bodies that are connected to each other, okay, through a joint, are the two joints are the two rigid bodies allowed to have any relative pose? Intuitively. So if you have, for example, one rigid body connected to another through a joint, is this rigid body, the first one, is it allowed to do anything? Is it allowed to have any pose? It's restricted, exactly. There are constraints. So a B degree of freedom joint would simply allow B directions, B components of the twist, and will constrain n minus B. Okay, and while n here, okay, it should be 6. Okay, so in the end, so 6 here. So and here, this is actually a type. It should be 6. So if you have a 1 degree of freedom joint, it means that you're able to move in one direction and you're constraining 5. If you have a 3 degree freedom joint, means that you can move in 3 directions and you're constraining 3, and so on and so forth. So a subgroup of SE3 is simply the constrained displacements of a rigid body that arise due to the presence of the joint. Now consider a joint that connects the two rigid bodies, body I and body J here, okay? And the displacement subgroup of SE3 that's associated with the joint is simply this. We're going to be denoting it by GI with respect to J. So when you see GI with respect to J, this corresponds to the joint that's connecting body I with respect to body J. Okay? It could be all of SE3. In that case, the joint is actually completely, it's completely virtual. There is actually no joint because the two bodies can move, okay, in SE3, but in general, okay, there will be constraining the motion. So the GIJ represents the set of all possible relative poses of body I with respect to body J that are allowed by the joint. And as a mathematical object is actually a B-dimensional Lie subgroup of SE3. Okay? A Lie subgroup means that, okay, it's a Lie group on its own, okay, and still it lives in SE3. Okay? So this is the idea of what the displacement subgroup is. Now, what do we call the configuration of a joint? The configuration of a joint is simply an element of GI. And GI itself is something else. It's not GIJ, it is something else. So GI is actually the configuration manifold of joint I. And QI here is the configuration of the joint. And GI mathematically is a B-dimensional Lie group that is isomorphic to GIJ. When we say isomorphic, means that there is a map that can take you from GI to GIJ. How does this map look like? We're going to be denoting this map by phi, this variable phi. So variable phi, you see, it will take an element of GI and it will map it to GIJ. So GI here, these are the joint configuration, while the elements of GIJ are actually relative poses of body I with respect to body J. So what you did so far is that we introduced two spaces, GI, GIJ, and one map between them. Okay? The example will show you. Okay? Take a look at the example, okay? And if it's not clear, ask me again. Now we're going to have 3 examples. The first one is a planar joint. Okay? So what does a planar joint mean? A planar joint is simply this idealization of one rigid body. So this is rigid body number 2. it's allowed to move relative to rigid body number one. Okay, so rigid body number one is this whole plane. Okay, this is the frame where it is, and rigid body number two is this box that can move on it. The planar joint is actually constraining the rigid body number two to move up and also to rotate around the X and the Y. So it's only allowed to rotate around the Z or move in the X and Y direction. So it actually allows for 2 translational degrees of freedom and for 1 rotational degree of freedom. Okay. About which axis? About an axis, let's call it in general Ni hat. In this case, Ni hat is simply the Z of frame 2, not the Z of frame 1. It's not rotating like this. It's rotating around, okay, Z2, okay? And Z2 is simply normal to the plane of motion. Okay? So this is usually what a planar joint is. In this example, we're going to be setting the Ni hat to be Z2. But in general, actually, you can flip all of the frames. For example, this whole setup can be actually like a board, okay, or on the ceiling, and you can have different frames. Okay. So in case that you really have a Z, that you're rotating around the Z, then the relative pose, okay, which is between body I and J, lives in Gij, that in this case is SE2. It's not SE3. This is actually called SE2, right? When you have only one angle of rotation and 2 degrees of freedom of motion, this is not SE3, this is SE2. While the joint configuration itself is actually Q1 and Q2 and Q3, where Q1 and Q2, they live in R2, they correspond here to the X and Y displacement. So if you see here, for example, Q1 is displacement along this axis, Q2 is displacement along that axis, while Q3 is simply the angle. So it's an angle from minus pi to pi. And this whole manifold, okay, this whole space is what we call Gi. Okay. So is it clear now the difference between Gi and Gij? Okay. The map between them, between Gi and Gij, okay, is given by phi. And in this example, for a planar joint, is given by this map. You see, it's a map that eats Q1 and Q2 and Q3, and in the end gives you a homogeneous transformation that describes the pose of body 2 with respect to body 1, and 2i with respect to j, or 2 with respect to 1 in this figure. Take a look at it until you digest it very well. Yes.
The information of the joint itself?
The Gi. This is the space where this Qi lives. The joint itself. The joint itself. Exactly. So here, you see, there is a joint. It's like, you might actually say there is actually no joint. I don't say a joint. I just say a body moving right there. Okay. But this is actually, it's like a joint. It's like, that's why I'm saying it's an ideal joint between that's constraining this body from going up, and it's constraining it from rotating around the X, the red axis and the green axis here of the body, attached to the body of 2. That's why we call it it's a joint. Okay. Again, first of all, make sure that you understand the math before going to the intuition.
Belongs to this Gi or the configuration.
Qi lives in Gi.
Joint configuration.
As we call it the configuration manifold of the joint, yes, or the joint configuration manifold.
Configuration of workspace.
It is the workspace, exactly. You see here the workspace, which is the rigid body number 2. It can only move in SE2. It can never go to SE3.
But what is the difference between Hij and Gij?
Hij is the element of Gij. Gij is the space. In this case, it's equal to SE2. Okay, you see here, for example, this is a homogeneous transformation matrix, right? Is this any homogeneous transformation matrix?
So the G.
Wait. Is this any homogeneous transformation matrix? No, this is not any homogeneous transformation matrix, because here you see I have zeros and 1. This actually zeros here, and this 1 means actually that I cannot have any rotation around X and Y. I can only have rotation around the Z. This is exactly what this means. Okay? So a homogeneous transformation matrix in general has here a full rotation matrix, but this is not. This is only a rotation matrix around one axis, and thus this is SE2, not SE3. SE3 would have here another example. And SE3, I can have here Q1 and Q2, and I can have here another number, not just 0. I can go in Z. But you see here I have only in 0, which means that this is why it's a homogeneous transformation matrix that's actually in SE2, not in SE3. Okay. Yes.
And do we need to write it as a 4-dimensional or a 4?
No, you don't. It's isomorphic to different stuff. Actually, you can write it as like a 3x3 matrix. Absolutely, you can do that. Okay. And in that case, actually, that's why, properly speaking, this actually should be isomorphic to SE2. Okay. But again, if you remember actually what was SE2? Remember what was SE3? It was the pair of R and psi. And then we put them in homogeneous transformation matrix as an embedding. The same here. You can actually here put them as an embedding in a 4x4 matrix or in a 3x3 matrix. It doesn't matter. In the end, the information is just that you have one rotation matrix in 2 dimensions around one axis, and you have 2 displacements. So this is one example of a planar joint. Another example is a prismatic joint. In this case, B is equal to 1. We're allowed to move around one axis. So we're going to be calling this axis again Ni hat, which in this case would be the x2 hat direction. So we're moving in the x2 hat in this picture. So the relative pose of Hij simply lives in the translation group. This is a subgroup also of SE3 that only has translations. It looks like this, you see. It doesn't have any rotation, okay? Or the rotation is fixed. And you're only allowed to translate in X and Y and Z, or in just one direction. Okay, here this is actually just in one direction. The joint configuration Qi lives in R. So R here, so the joint displacement can be any value in R. Okay. And the map that takes you from this one number to this 4x4 matrix is given like this. Make sense? Another example that's completely degenerate. It's the floating joint. The floating joint is simply a joint that has 6 degrees of freedom, that in this case, the relative pose will be all of SE3, and the joint configuration is actually Hij, and the map that takes you from Qi to Hij is given by the identity map. It's just a degenerate case. Okay? You might think, okay, why do we need to introduce this? This is actually how softwares do it. But when you're actually using the MATLAB toolbox, you're going to find that you can add between 2 frames something called the floating joint that will allow this joint to fly. Okay? So this is usually the case that we have with robot arms. We have, for example, 1 degree of freedom joints between bodies. Can anyone guess of a use of this planar joint and a use of this floating joint? For what? For what kind of scenario? What can you model with it? Sorry? What can you model with a planar joint? A robot on the ground, exactly. A mobile robot on the ground, like this picture. Like this picture. Okay. Provided that there's here a constraint, provided that the wheels that are allowing this robot to move don't have any constraints. Okay, stuff like called holonomic constraints or non-holonomic constraints. We're not gonna go into details of that. Look, but if you have a mobile base that's allowed to move in all directions and rotate around, okay, the center of the base, then you can actually model it as simply an ideal planar joint. What about the floating joint? A drone, for example, with a robot arm. What else? An underwater vehicle with a robot arm. A space robot with a robot arm, and so on and so forth. You can model this base floating as a floating joint. Okay, this is actually how the software, some software tools allow you to do this. Okay, so make sense? Clear? Easy, right? So that's one. Okay, so this is one concept, the displacement subgroup, and it allows you to discuss all of these cases. If we have configurations, if you have a map between the configurations, and these are Lie groups, what do you expect? What should come next? A map between the algebras, exactly. If this is a map that talks about the Q and the H, what do you think the other map will talk about? The algebras will have. Yeah, but what kind of information will be there? Velocities, exactly. If this is a map between the configuration and the pose, then later on we're going to have a map. We can build a map. Okay, so actually we're going to have an induced map on the velocities that we're going to be denoting it by iota. So this is an I without a dot. It's actually called iota. And it's also it has here a subscript I. So when this also phi has a subscript I because we're gonna describing joint I. And this is also iota that describes joint I. And this is a map that eats an element of the Lie algebra of this group, and it maps it to the Lie algebra of that group. Okay. What lives in let's start with this one. What lives here in this Gij? The relative pose between body I and body J. What do you think will live in the algebra here? The twist between body I and body J. Okay. And this is Gi. If here you have Qi, then this will be Vi. Okay, so this will be, you remember how the velocity is related to H dot? The twist, how is it related to H dot? Left translation, right translation, and you have the tilde form, right? And the Vi is also related to the Q dot, okay, in some way. Okay.
It should be relative motion. Right?
Which one?
Yeah, it should be relative, right?
It's exactly, it's the relative twist. Which one? Here. This is because this is just a notation that actually we're saying that this is the velocity of joint I, the joint itself. It's like the joint itself that's connecting body I to body J. Okay, we're just going to be noting it by joint I.
What is expressed or relative to what?
It doesn't need an expressing. It has numbers of its own. That's the idea of the joint. With respect to the joint, yes. With respect to the joint, yes. Okay.
So there is a frame in this joint, and it moves relative to it. Should be something.
You're gonna you'll wait. Wait.
Zero.
You'll see what that means with an example. Question? There was a question here. No? Okay. Again, let's look at the example and see how it looks. So first of all, before moving on, is that Gij, okay, with this element where the twists live, is actually 6 number, right? It's actually in R6. And the Vi, you're going to be seeing that it's actually in RB. So in the end, we're going to have just 3 B numbers, okay? B, okay, values. And the map between RB to R6 is simply 6 times B matrix. So you're going to see here, we're going to usually have a 6 times B matrix that will map the Vi to the Vij. Okay, so this is in general. This map iota is equivalent to just this matrix S. And this S will be very important to what we're going to be doing later on, inshallah. Now let's look at the examples. Okay, one more thing. Okay, so this is the phi that maps the Gi to the Gij. This is the iota that maps the Lie algebra I to the Lie algebra Ij. And now the last thing that we need is simply a relation between the Vi and the Qi dot. We're going to have another map called chi. Okay, that's a function of Qi, and it will map the Vi to the Qi dot. With these 3 pieces of information, you can model any joint. Okay, so that's the thing. Only if you identify these 3 maps, you can model any joint, any ideal joint that we're going to be using later on. Now let's look at the example. So the planar joint, let's go back to the planar joint. This was the configuration of the planar joint. You all agree? You have Q1 and Q2 and Q3. So the joint velocity are 3 numbers, Vx, Vy, and omega z. They are simply rotation around the z and translation in the x and translation in this y. Okay. So you see why we're saying here it's only Vi, because they are already, okay, describing the motion of this frame. Okay. They're already expressing it in this frame. We're not going to be expressing it in somewhere else. Okay. So you see, now we have a map that goes from these 3 numbers to the whole twist. What does this map look like? It looks like this. Check it for yourself and see whether it makes sense or not. It has a revolution around Z, but it also has X and Y motion. This is a planar joint. This multiplied by this will give you 0. This multiplied by this will give you 0. This multiplied by this will give you omega z. This multiplied by this will give you Vx. This multiplied by this will give you Vy. This multiplied by this will give you 0. So in the end, what does the twist look like? 0, 0, omega z, Vx, Vy, 0. This is the twist that's allowed by the joint. Make sense? Makes sense. So what is the map that will take you from these three numbers to the Q1 dot and Q2 dot and Q3 dot? It's actually given by this. Take a look at it and see whether it makes sense or not. Of course, it's a rotation matrix, but here we just say it's a map that will take you from these three values that correspond to the joint and to the rate of change of the joint configuration. Okay, and this is the map that takes it. Of course, it's in the end, it's just a rotation matrix. Okay, make sense? So here, Q1 was motion in this direction. Q2 was motion in that direction. And Q3 was rotation around the Z of the frame 2. So if we call the velocity rotating around the frame 2 to be omega Z, then simply Q3 dot is equal to omega Z. This is the third equation. Q3 dot is omega Z. And the motion in this direction and that direction are related to the motion in this direction and that direction by simply a cosine and sine. You have cosine minus sine, sine, cosine, because you're just rotating, okay, the velocity.
Exit is the forward for the forward, right?
In the x2 direction, yes. So Vx is in the x2 direction, and Vy is in the y2 direction. Okay. Make sense? So that's the planar joint. What about the prismatic joint? You just have one value. I have Vi and Qi dot, they are actually the same thing. So the map between them is actually identity in one direction. So here the map that will take this one direction and give a twist is simply 0, 0, 0, and simply 1 in the direction in which I'm going to be moving. And in this case, the direction you're going to be moving is in the x direction. So you have here in the x, the first one.
In the previous slide, this was Jacobian, right?
We have introduced this notation. Okay, but it is related to it, yes. You're going to see what the Jacobian is later on. But so far, we're talking about one joint only. Okay, make sense? After that, the degenerate case, which is the floating joint. So the joint configuration is Qi, and it's the same as Hij, as we said. The joint velocity, Vi, and the relative twist, they are the same thing. So actually the map iota is identity. Then we're left with one thing, which is the map that will take me from the V, the relative twist, or in that case, which is the joint velocity, to the H dot. What is this map? It's this one. Okay. If I want to represent it as a map, as that's a function of the Q, and the Q in this case is Hij, and it eats a vector, okay, in R6. Then simply, I would take this vector, apply the S tilde map. What was the S tilde map? What was the S tilde map? It would take the 6 numbers of a twist and put it in a 4x4 matrix. You remember? The tilde form of the twist. This was the S tilde. Right? And after that, I have a 4x4 matrix here. I multiply it by the Hij inverse. I get the H dot. So all of this, what I said here by words, is what we're going to be calling a map chi.
The tilde means symmetric.
No, if only for SO3. What we're doing here is what's called an abusive notation. So if you give me 3 numbers, call them, for example, omega, or call them psi, and I do a tilde form, because they're 3 numbers, they get transformed into a skew-symmetric matrix in 3 dimensions. But if you give me 6 numbers and I give them a tilde form, what's meant by this is the 4x4 matrix that has the first 3 numbers in skew-symmetric form and the second 3 numbers next to it, and the rest is zeros. So this is called the abusive notation. Okay. This is the tilde. So the S tilde, you're going to find it was mentioned in the slides. It's the map that is a V and give you a V tilde. This is the name of the map. Okay, you're just introducing some stuff. You have to be very careful, you know, where to do this. Yeah, you're going to appreciate this introduction of all of these maps once you go to the code, because once you go to the code, intuitively they are the same thing. But once you go to the code, having 3 numbers is different from having a skew-symmetric matrix. Having 6 numbers is different from having a 4x4 matrix, and all of the dimensions they have to match, and so on and so forth. So this is the idea of introducing all of these maps. Make sense? Okay. There is one thing we haven't discussed about it. What is it? There's something that was completely missed from what we discussed. What is it? What did we miss here? We did not talk about what type of joints. Revolute. We talked about prismatic. Prismatic are easy as this, but we haven't talked about revolute joints at all. And when we have robots, most of the robots are actually made with revolute joints. Yes. Yeah. Okay. So what you're going to be seeing now, this is what we're going to be doing now. What we're going to be doing now is that these maps, the map that will relate the joint configuration to the H and the joint velocity to the hole twist, can be actually geometrically represented by what's known as the exponential map of a Lie group. Okay, it can be very elegantly. We can do it very elegantly, and this elegance will actually, we're going to be seeing it. First of all, is that revolute and prismatic joints will be exactly the same. Exactly the same. I mean the same. Okay, there will be a unified treatment for both. We're not going to have any predefined choices of the body fixed frames. For example, when we say I have body I and body J, and there are 2 frames on them, we haven't said that frame I should be like this or frame J should be like that. Has anyone heard about the DH parameters? Okay, if you took any course on robotics and you know what the DH parameters are, they're a very bad way of doing robotics, in my opinion. Because you need to say, okay, the frame needs to look like this, and it needs to be placed in that place, and so on and so forth. So you have predefined choices of what these frames are. But in this case, what we're going to be doing, we just tell you, put the frames wherever you want, however they will look, okay, however they should look like. Okay, so that's how general it is. Forward kinematics will be very clean and very modular, as we're going to be seeing next time, inshallah. And also differential kinematics will be completely naturally following from what we do. And thus, we're going to be looking at now what the exponential map is. There's just a bunch of, okay, terminology with, hopefully with the intuition. They're actually very intuitive, exponential maps, what they are. And that's why we're going to be starting with SO3 first. And hopefully we're going to have time to go to SE3 as well. So what are the exponential coordinates of rotations that are described by SO3? Take this intuition. Let's start with a frame B that has unit axes XB, YB, and ZB hat. Okay, the ones in purple here. And they are attached to a rotating body. So assume that this frame is actually rotating. The purple frame is rotating with the body. And the blue frame here is fixed. It's not rotating. The angular velocity is a vector that describes the instantaneous rotation of frame B with respect to frame S, and is given by omega bs. And omega bs, okay, is simply, it has a direction and a magnitude. You know, any vector has a direction and magnitude, right? And if you multiply the direction with the magnitude, you get the vector itself. So this should be familiar. So n hat is nothing else than the direction of the angular velocity, and theta dot is simply the magnitude of this velocity. So omega bs is simply, okay, and it's like a 3 vector, while n hat is a unit vector, and theta dot is just a number that describes the magnitude of this vector. This should be familiar to everyone, that the rate of change of the orientation is related to this vector, okay, by the omega tilde, the skew-symmetric form of omega, if you express it in the S frame, because here it's only abstract. Okay, this is just a vector, and I can look at it from either the fixed frame or the rotating frame. Okay, so, but here this is abstract, and this is with numbers as a skew-symmetric matrix. If you represent it in the S frame, this is the expression that corresponds to the R dot. Now this is the new stuff. If omega is fixed, assume, for example, that n hat is constant. It's not changing. And theta dot is equal to 1. So we're looking at a scenario that we're going to be rotating around one frame. Okay, a general rotation does something like this. This is a general rotation. You see that the direction around which you're rotating is changing, right? But if I say I'm going to rotate around, for example, this axis, let's say this is the body and this is the axis. So actually, I'm going to rotate something like this. You see? So you see this rotation I'm describing now is actually around one axis only. That's not changing. It's fixed. This is actually what this means. And let's assume theta dot is equal to 1, just for simplicity. So in this case, omega hat is simply a constant. So I have an equation that looks like r dot is equal to a constant matrix multiplied by r. If you have any knowledge about linear systems, this should ring a bell, right? If you have like something like x dot is equal to some constant matrix A multiplied by x, you know that this has a closed form solution that looks like this. If you know it, you know it. If you don't know it, you can know it just in this case. You don't need to, you can relate it actually to the general case later on. It's very easy. So this equation, in case omega is constant, actually has a closed form solution. It's a very elegant one that looks like this, simply with what's known as the exponential map. So you see here I have an exponential of n tilde multiplied by t. So r at any function of time, okay? If you tell me this is the direction around which I'm rotating, so this is n hat, it's constant. You tell me what is n hat, you tell me what was your initial configuration, and you tell me what is the configuration after 1 second, after 2 seconds, after 3 seconds. I just plug in this equation, and I can tell you exactly what the rotation matrix will look like. Tilde is not the same as the hat. You see here? So n tilde is simply s of n hat. So n hat is a unit vector. N tilde is the skew symmetric matrix that corresponds to this vector. Properly speaking, it should be n hat tilde on top of it, but it will be too heavy. That's why this does this, simplicity. Okay, so n hat is just a unit vector. It's 3 numbers, but they have a magnitude of 1. And n tilde, simply the skew symmetric form that you should be familiar with.
So this term in the power of the exponent, it's a matrix.
It's a matrix. Yes. So yes, that's a good point. So this is r dot is equal to a 3 by 3 matrix multiplied by r. If you have an x dot is equal to a, where x, let's say x, state space form. X dot is equal to ax, where a is a constant n by n matrix. What is the solution of it? It has x of t is equal to e a t. This is a matrix exponential multiplied by x at time 0. Exactly the same here.
Is the direction of this omega?
Yes.
This is the relative motion from B to S.
Exactly.
This is for this omega.
Exactly. Yes.
If the rotation is around one axis.
That's right. Yes, absolutely. That's why here that has to be fixed. The direction has to be fixed. You're not changing. Absolutely. The theta dot is equal 1 just to see really clearly that this is actually just a function of t. There's no theta. But actually, if you see here, if theta dot is equal to 1, then theta as a function of t is simply t. You can actually remove the t and put in instead of a theta. And that's exactly what we're going to be doing. So here, I can just easily replace the parameter and just call this r of theta instead of r of t. And simply what you see here is that we're able to parameterize a rotation matrix by 2 pieces of information, an n hat and then angle theta. So which means that if you give me any rotation matrix, I can give you instead 1 unit vector and 1 number that corresponds to that rotation matrix. Written like this is actually the other way around. You give me the angle theta, and you give me the direction, I plug them in this equation, and I get the rotation matrix. The question is this map invertible? You can actually invert it, yes. But it's actually, you're going to be seeing now, it's surjective but not injective. Okay, so this map is not 1-to-1. Okay? There's no theta dot. The theta, not the theta dot. There is no omega now. We actually derived from it something else. we integrated this equation. And thus we see here we have a theta and the n. But if you remember, the omega itself was two things, was the direction and theta dot. And theta is the integration of theta dot, right?
But in general, I can have the rotation matrix.
Yes. But you see, you cannot have only a theta and get a rotation matrix. You need to also specify around which axis you're rotating. The direction. You're rotating around X or Y and Z. You need to specify. That's the n here. You see, you tell me the angle, and you also need to tell the direction. Yes. Exactly. Exactly. Absolutely. Yes. Okay. Is that clear for everyone? So
some integration for theta, right?
yes.
But should be something the theta is a group.
You see here, theta? Yeah, theta dot is a number. Theta dot lives in R, and in R you can do integration. You have normal manifold. Theta dot lives in R. Theta dot lives in R. And theta lives from minus pi to pi. You can integrate normally. Yeah, you can integrate normal. Yeah, once you get to what you do actually is that once you reach the end, you just identify the pi with minus pi, and you just start, going around.
I need to make
That's exactly what moving from R to the circle does. You do the modulo of the 2 pi exactly, or modulo of minus pi. So all what we did so far is what we were actually describing the direction in the S frame. If you describe it in the B frame, you get everything exactly the same. It's just the order will differ. Okay. So here, this simply what you can look at this equation, you see that. If we start from some initial rotation matrix, okay, let's assume this is the identity, for example. And I say I want to rotate around this axis with an angle of 45 degrees. What is the rotation matrix? I can calculate it from this expression or from that expression, doesn't matter. I just need to know which frame I'm going to represent it around. Okay. If you do the same, also not around this axis, but around that one or this one, or even any fourth frame that's combination of all three, n hat can be any frame. Of course, the only restriction here is that it should be constant, it should not change. Make sense? Okay. Now, this map is surjective but not injective. Okay. And this is just the confirmation to that. You should know what this means. The exponential map that we just described will actually, what it is doing is that it's taking an element of SO3 and it's giving us an element of SO3, capital SO3. It's taking an element of the algebra, the omega tilde, and it's spitting out a full rotation matrix. Okay. So this is known as the exponential map. And in the case of SO3, this exponential map has a very beautiful closed form solution. That lives in small SO3 or big SO3? The Lie algebra, it's omega. Yes, that's right. Yeah, that's a very good point. But where theta dot, okay, is just a number, right? And R itself and theta is also another number. So there are two numbers. They're not the same, right? So there are two numbers. Theta dot is a number and theta is another number. But in the end, if you multiply theta dot by n, you get the omega. But if you multiply the theta by the n, you get another element of the algebra. I know it does not have a unit of velocities, but it's still a skew-symmetric matrix and still lives here. It's a different object. It's a very good point. It's a very good catch.
Theta dot, it was tangent space for SO3.
It was R. Theta dot lives in R. It's just a number. You're talking about theta dot. No, wait. No. You see what theta dot was? It was just a number.
It is represent this if I have mapping S, for example, it will be omega skew matrix omega.
Ah, okay, I see your point. No, it's just a number. It's just a number. I see your point now. So you see here, the frame B is rotating around this axis with a speed of 5 rad per second, or 100 rad per second, or minus 100 rad per second. Does this mean there is an angle, or just a number? That's it.
So here it is R.
It's an R, yeah. Theta dot lives in R. Just R. I know you're bothered about the dot bar, right? Yeah, that's right. But in R, the tangent space of our real numbers is actually the real numbers. You remember when we talked about Rn? The tangent space to Rn at any point is actually Rn itself. And the dual space to Rn is also Rn itself. You start to lose all of this stuff when you start to book Rn. Okay? So what we have right now is that we have a closed form expression that if you give me any n, okay, the n hat, that's a unit vector, and the theta, which is an angle, I can just plug it in this equation, okay, that looks like this, and I can give you back a rotation matrix. And this expression actually is called the Rodriguez formula. Okay, so the Rodriguez formula, simply something, it's very easy to implement, okay, on MATLAB or in any Python. It's one line of code that takes a unit vector and an angle, okay, from minus pi to pi, and it will spit out a rotation matrix like this. What do we do with this rotation matrix? If I multiply it by before or after, okay, by some rotation matrix, another rotation matrix that corresponding to B with respect to S at time 0 or at angle 0, it will tell me what is the rotation matrix corresponding to rotating around this axis and hat by an angle of theta. Make sense? So there are two aspects here. Make sure that you understand both of them separately. There is the mathematical part and the intuitive part. The intuitive part is there's this picture. I have a rotation. I'm rotating around one axis by some angle. And the math is simply the Rodriguez formula given by this. Okay? And there's another aspect to it, which is the important one, that is the abstraction. What we did here with the exponential map, we said we can actually do it for any Lie group. I can define a map that goes from any algebra to the Lie group of that Lie algebra. Okay? And thus, what do you think will be the next thing? Going from SO3 to SE3. That's the natural thing that we did, right? So since we said that an angular velocity vector that corresponds to the relative angular velocity between body B and body S, okay, or the body attached to frame B and the body attached to frame S, can be viewed as the multiplication of some direction and some theta dot, where n dot hat is the unit rotation axis and theta dot is the rate of rotation around it. We can also interpret a twist as 6 numbers that we're going to be calling a screw axis and a velocity q dot about that screw axis. And that's the picture you see over there. Okay? So the relative motion between body B and body S, or frame B and frame S, can be interpreted, the relative twist between them can be seen as 6 numbers, SBS, multiplied by q dot, where q dot will be the motion around that axis. Okay? And we're going to be seeing exactly what do we mean by that. You actually have 3 cases when you describe this. You can have pure translation. Okay? So I have this body that was like this initially and it moved like this, or like this, or what's the third one? Like this, right? So these are the 3 directions. Or like this, right? Right? Or like this. Okay? I can have any direction. I can translate in any direction in space. So you see here, if you have pure translation, simply you can say that n hat is the translation axis around which you move, and q dot is the linear velocity along this screw axis. Okay, so I'm moving in this direction by 5 meters per second. I'm moving in this direction by 10 meters per second. I'm moving in this direction by minus 5 degrees per second, and so on and so forth. Okay? So that's exactly what this means. Make sense? What is the screw axis that corresponds to it? It's simply zeros on top, 3 zeros, and the n hat on the bottom. This is how the screw axis looks like. If you have pure translation. Pure rotation are a little bit trickier. We have something that looks like this. So pure rotation means that frame B is rotating around frame S. Okay, it's actually rotating around this axis by an angle. It's not rotating around any one of these axes. It's rotating around somewhere else. For example, you can take a look at this body. Let's assume that this is the axis I want to rotate around by 90 degrees. This is the motion I'm going to be doing. You see? I'm not doing like this. I'm not rotating around this axis by 90 degrees. I'm rotating around this axis by 90 degrees. Okay? Or by 2 rad per second, or 3 rad per second, and so on and so forth. Okay? So I have an axis, okay, and I have a rotation around that axis. So I have n hat, and I have the q dot. And if you want to build this, okay, screw axis that corresponds to it, is simply put the n hat on top and take the cross product between n hat and any point on that axis. Any point. Okay, I can choose this one, that one, this one, even the one at infinity or at minus infinity. I can take any point, and I'm going to get the same number here. Okay. There's a lot of math, of course, that we're skipping here, but this is just, you know, the calculation stuff that we're going to be needing to do. Which time we have? Okay, we're almost there. And there's a third type. It's actually a screw motion. A screw motion is actually, it's a translation and the rotation around the axis. It's like exactly what you call a screw. You know what a screw looks like? It's neither rotation nor translation. Actually, it's like translation in an axis around which you're rotating. This is actually called the screw motion, and you can still represent it by a screw axis. And that's the name, actually. Screw axis came from this terminology. Okay? And you can find it in the book if you're interested.
Direction here, direction.
One direction only, and you're going to have a point on the axis, and you're going to have a third thing, which is actually the pitch. It's like exactly when you have what's it called? As helix, when you have a helical motion. Exactly, they're related, exactly, by the pitch. Exactly. And this extra parameter will appear here in the screw axis. Okay? But still, you're going to have 6 numbers. Then you don't have a exactly. It's not screw motion if it's independent. But the thing is, there is actually a theorem, and this is it's actually a theorem. What's it called? It's either attributed to someone called Chassel or someone called Poisson. Okay, there is just a dispute in the literature. Who's it attributed to? Let's give it to both. There is actually a theorem that says if you give me any twist, I can represent it by some motion around a screw axis. So I can actually define from, if you give me any 6 number that correspond to the motion of body B to body, okay, body B to body S, okay, and they are not dependent at all, I can always find some axis around which this motion is equivalent to a screw motion. However, the trick is that this is only instantaneous. After it changes with half a second or like infinitesimally, the axis itself which will change. Okay, it's actually something called, what was it called in mechanics?
General kind of motion as a rotational.
Exactly, that's exactly what had a name. What was it? Center of rotations. Instantaneous center of rotation. Yeah, exactly. It's exactly the same. The instantaneous center of rotation in 2D can actually be generalized to 3D by what's known as Chassel or Poisson theorem. That's exactly it. Yeah. So now we have 2 things. We have the q dot, which is the velocity around which you rotate or translate, and you have the axis, which is the screw. What you would need to do now is that if you have these coordinates, I can simply define an exponential map on SE3 that will eat these 2 pieces of information and give us in the end a homogeneous transformation matrix that I can multiply from the left or from the right by the initial configuration, and it will give me the configuration after I've moved with some variable q. Okay. And what we're talking about here is an exponential map. Okay, it's a generalization of the exponential map on SO3. It's a map from SE3, small SE3 to capital SE3. It's surjective but not injective, the same idea. And it has also a closed form solution. If you have a pure translation, it's very simple. It looks like this. Okay. So my screw axis was simply zeros on the top and v, that's some number v on the bottom, where v here was actually a unit vector. It had the magnitude equal to 1. So you take this v, multiply by the q, this is your translation, and the rotation is simply identity, and you have zeros and ones down. If you have the pure rotation part, it will be trickier, okay, but still it has a closed form solution. All of this, what you see here, in the end is nothing else than just some number, okay, 3 numbers. It's a 3 vector, all what you have here. Actually, there's a typo here. This actually v should be here, not before, because in the end, this is a 3 by 3 matrix that you multiply by the 3 by 1 vector, giving you a 3 by 1 vector. And what you have here as the rotation matrix is nothing else than the exponential map of the SO3. So actually, the Rodriguez formula is used inside of this big exponential map. Okay. So we're done. Okay. So there's a lot of new information here. Okay. But you're going to be seeing next week, inshallah, when we go to the applications, is that it all boils down to just specifying what the S is. That's it. If you say what the screw axis of all of the joints that you have on your robot is, you're done. The rest is just coding. Okay, it's very trivial. You know, it's a very standard code. We're actually you're gonna be given. You're gonna be using it in the project, and you're gonna be straightforward. You can calculate the homogeneous transformation of the end effector or even of any frame on your robot with respect to the base frame. And after that, the rest is just multiplying homogeneous transformation matrices by each other and so on and so forth. This is at the configuration level. We have the same. We're gonna be doing the same at the differential level when we look at the twists. And we're going to be looking at what's known later on as the Jacobian and so on and so forth. Okay, so that's it for now. Okay, so any questions? We have 3 minutes. No more questions? Okay, so let's stop. Jazakumullah khair.